Imagine standing on a beach, toes in the water, waves politely licking your feet, like the ocean is saying hello. Now imagine that same water stretching downward, not for meters, not for kilometers, but for distances so absurd that your brain quietly files a complaint and asks for a coffee break. This is where our story begins, not at the shoreline, not even at the continental shelf, but far below anything humans were ever supposed to casually know about. A place so deep that if Earth were trying to hide secrets, this is where it stuffed them and threw away the map. Welcome to the Hadal Zone, the deepest region of the ocean, named after Hades, which should already tell you this is not a spa destination. If this slow reflection on what we've learned from exploring Earth's most extreme ocean zone helps you unwind tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this calm science can reach more people who drift off to sleep with the deep sea. For most of human history, the ocean was deep in the same way the sky was tall. People knew it went on forever, but nobody had the tools or the courage to check. Early sailors dropped weighted ropes overboard, watched the line vanish into the water, and eventually shrugged when it stopped being practical. At a certain point, the rope ran out, patience ran out, and someone probably said, "Yep, that's deep enough to be unsettling," and went back to worrying about pirates. For centuries, the deep ocean existed more as a concept than a place, a watery abyss where monsters were rumoured to live because, frankly, nobody could prove otherwise. The first real cracks in our ignorance came with the invention of echo sounding in the early 20th century. Instead of guessing with ropes, scientists began sending sound pulses straight down and listening for echoes bouncing back from the seafloor. Suddenly, the ocean wasn't just deep, it was uneven. The seafloor wasn't a flat, boring slab, but a dramatic landscape with mountains, plains, and massive trenches that looked like Earth had been clawed by something with serious anger issues. These trenches were deeper than anyone expected, plunging far beyond what intuition considered reasonable. One of them, the Mariana Trench, quickly became the overachiever of the group, stretching nearly 11 kilometers down. That is taller than Mount Everest is high, which feels unfair to mountains that worked so hard. At first, scientists assumed nothing could live down there. The logic seemed solid: crushing pressure, eternal darkness, freezing temperatures. It sounded less like a habitat and more like a cosmic punishment. The deep ocean was imagined as a lifeless void, a geological basement where nothing moved except maybe the regrets of adventurous submarines. This assumption wasn't born from arrogance, but from limited experience. Humans tend to judge habitability based on whether we personally would enjoy it, and the Hadal Zone scores very low on vacation brochures. Then came the Challenger expedition in the late 19th century, which didn't actually reach the deepest parts, but shattered one crucial myth. Life was found at depths previously thought impossible. This discovery was like finding ants in a freezer and realizing nature did not read the instruction manual. The idea that the deep ocean was empty began to wobble, though the very deepest zones remained untouched, protected by technological limits and healthy fear. The true turning point arrived in the mid-20th century with "now that we know the Hadal Zone exists." The next logical question is what it actually is, beyond being very, very deep, in the same way space is a bit chilly. The Hadal Zone is not just the bottom of the ocean. It is a specific, extreme region that begins roughly 6 kilometers below the surface and extends all the way down to the deepest trenches on Earth. This is not a gentle slope or a gradual fade into darkness. It is a sudden geological plunge, a vertical commitment that the planet made and never apologized for, unlike most of the seafloor, which spreads out in broad plains and rolling hills. The Hadal zone is almost entirely made up of oceanic trenches. These trenches are long, narrow depressions that slice into the seafloor like scars. They are not evenly distributed either. You will not find one casually off every coastline. Instead, they cluster along specific regions of the planet, forming arcs that trace the restless boundaries of tectonic plates. If Earth had a stress map, trenches would be the deep wrinkles where pressure has been building for millions of years. To understand why these trenches exist, we need to talk about plate tectonics without turning this into a classroom flashback. Earth's outer shell is broken into massive slabs called plates. And these plates are always moving, even if the motion is slower than a snail wearing weighted boots. When two plates collide in the ocean, one of them usually loses. The denser plate bends and slides beneath the other in a process called subduction. This bending does not happen gently. The sinking plate drags the seafloor downward, creating a trench that deepens as the plate continues its slow descent into the mantle. This is why trenches are not random. They mark zones of planetary tension where Earth is actively recycling its crust. The Hadal zone is essentially the visible edge of this recycling system, the place where the surface world hands material back to the planet's interior. If Earth were a factory, trenches would be the loading docks where old crust is fed into the furnace for repurposing. It is efficient, dramatic, and completely indifferent to our sense of scale. The Mariana Trench, the deepest of them all, exists because the Pacific Plate is diving beneath the smaller Mariana Plate. This interaction has been happening for tens of millions of years, gradually deepening the trench, like a slow-motion demolition. The result is a chasm so deep that it warps our intuition. Drop Mount Everest into it, and you would still have room for more mountain. That comparison never stops being funny because it sounds illegal, like the planet is violating some unspoken rule about fairness. But trenches are not just deep holes. They are dynamic geological features. As plates grind past each other, stress builds up, releases, and reshapes the surrounding region. This movement can cause the trench walls to slump, fold, and fracture. Sediment from above slides downward, collecting at the bottom like crumbs swept under a rug no one plans to lift. Over time, this creates a layered archive of material from the surface world, slowly accumulating in one of the most inaccessible places on the planet. What makes the Hadal zone unique is not just depth, but geometry. Trenches are narrow compared to their length, forming long corridors rather than wide basins. This creates an environment that is more enclosed and isolated than most of the ocean floor. Water circulation behaves differently here. Materials that fall in are less likely to escape. It is a geological trapdoor, collecting whatever gravity and time decide to send its way. The shape of trenches also affects how we explore them. Mapping these regions is notoriously difficult because steep walls and extreme depths interfere with traditional surveying methods. Sound waves scatter unpredictably, and equipment must navigate vertical drops that feel less like seafloor exploration and more like urban canyon flying. Every detailed map of a trench is hard-won, pieced together from careful passes and patient data analysis. There is also an emotional component to understanding trenches. They challenge the idea that Earth is a stable, finished object. Trenches are proof that the planet is still under construction, still breaking and reshaping itself beneath the ocean's surface. The Hadal zone is not a quiet basement. It is an active fault line between what Earth was and what it will become. So when we say the Hadal zone is Earth's deepest ocean region, what we really mean is that it is the surface expression of colossal forces at work. It exists because plates collide, bend, and descend, cracking the seafloor open like a dropped dinner plate that no one bothered to sweep up. It is a reminder that depth is not just about distance. It is about process, pressure, and a planet that refuses to sit still. If depth is the address of the Hadal zone, pressure is its personality, and it is not a friendly one. Pressure is the single most defining feature of the deep ocean, the invisible force that turns ordinary matter into something that needs to seriously rethink its life choices. On land, pressure is polite. It presses down gently, just enough to keep us anchored without us ever noticing. We live our entire lives under it and never say thank you. In the deep ocean, pressure stops being polite and starts making demands. Pressure exists because water has weight, and the ocean has a lot of it. Every layer of water presses down on the layers below, stacking force upon force. As you descend, you are not just moving through space. You are moving into a growing column of water that is increasingly unimpressed by your presence. With every step downward, the squeeze intensifies, like an ever-tightening hug from a planet that does not understand personal boundaries. At the surface, your body is in balance. The pressure inside you matches the pressure outside you, and everything behaves as expected. Descend a little, and that balance begins to shift. Air spaces compress, gases dissolve. Materials that feel rigid at the surface start to reveal that rigidity was more of a suggestion than a rule. By the time you reach the depths associated with the Hadal zone, the pressure is no longer something you can imagine intuitively. It is measured in hundreds of times the pressure we experience every day. Numbers that look impressive on paper and actively hostile in reality. The human body is not built for this. Our bones feel solid, but they are not designed to resist uniform compression from all directions. Our lungs are full of air, which is wonderfully squishy under pressure in all the wrong ways. If a human were somehow exposed directly to Hadal pressures without protection, the outcome would be immediate and extremely final. This is not a dramatic exaggeration. It would be physics doing exactly what physics always does, without malice or hesitation. Like a soda can under a hydraulic press, except the soda can at least had a warning label. What makes pressure so fascinating is that it does not just crush things, it changes them. Chemical reactions behave differently when molecules are forced closer together. Structures that rely on rigid shapes can fail, while flexible ones suddenly become superior. Pressure does not care what something is made of, only how that material responds when squeezed relentlessly. This is why materials science becomes critical in deep-sea exploration. Metals that perform beautifully on land can behave unpredictably when subjected to extreme compression. Tiny flaws become catastrophic weaknesses. Bolts, seams, and joints must be designed not just to resist force, but to distribute it evenly, like a diplomatic negotiation with the ocean. Pressure also behaves with a kind of cruel consistency. It does not fluctuate wildly from moment to moment. Once you are deep, it is always there, pressing equally from every direction. There is no safe side to lean toward, no direction where it eases up. This uniformity is part of what makes it so dangerous. Humans are used to directional forces. Gravity pulls down. Wind pushes sideways. Pressure in the deep ocean surrounds you completely, turning space itself into an adversary. Understanding pressure changed how scientists thought about the deep sea. Early assumptions imagined it as an empty void because it seemed unreasonable that complex structures could exist under such conditions. But pressure does not automatically mean destruction. It means adaptation is mandatory. Anything that exists there must be built at every level to tolerate constant compression. This realization shifted the scientific conversation from "nothing can live there" to "what would life have to be like to survive there?" which is a much more interesting question. Pressure also creates a barrier to exploration that is psychological as much as technological. It is one thing to imagine darkness or cold. It is another to imagine an environment that would crush unprotected machinery as casually as stepping on a cardboard box. Every deep-sea expedition is, at its core, an argument against pressure. A claim that human engineering can temporarily carve out a pocket of normalcy in a world that rejects it. The Hadal zone teaches us that pressure is not just a measurement. It is a shaping force. It dictates design, limits behavior, and filters out anything that cannot cope. It is the reason exploration vehicles look the way they do, why experiments must be carefully sealed, and why the deep ocean remains one of the most challenging places humans have ever tried to visit. In the end, pressure is the gatekeeper of the deep. It does not roar or threaten. It simply waits, applying its force patiently, endlessly, reminding us that the deeper we go, the more the planet insists on having the final say. Light feels like a basic feature of existence. We wake up to it, measure time by it, and panic slightly when it goes out unexpectedly. On the surface, sunlight pours down so generously that we rarely think about its limits. But the ocean has a very different relationship with light, and it becomes clear almost immediately once you start descending. Sunlight does not fade politely. It vanishes in stages, each one taking a familiar version of reality with it. Near the surface, light behaves as expected. Colors are vibrant, shadows exist, and vision works the way our brains are comfortable with. But water is not a friendly medium for light. It absorbs and scatters photons efficiently, like a sponge with trust issues. As you go deeper, longer wavelengths disappear first. Reds fade, then oranges, then yellows, until everything takes on a cold blue tone. Eventually, even blue gives up. At a certain depth, sunlight is simply gone. Not dim, not dusky, gone. By the time you approach the Hadal zone, the idea of day and night has completely lost meaning. There is no dawn, there is no dusk, there is no noon. Darkness is not an event here. It is a permanent condition, as stable and unchanging as the pressure that surrounds it. This is a world where the sun has been absent for so long that nothing expects it to come back. If light were a person, this ecosystem would have stopped checking its messages millions of years ago. For surface life, sunlight is more than illumination. It is the foundation of food webs. Plants capture it, store it, and pass that energy upward through ecosystems. Remove sunlight, and the entire system collapses. Or at least, that is what we assumed for a long time. The deep ocean forces us to confront a more uncomfortable truth. Life does not need sunlight specifically. It needs energy. And if the sun is unavailable, evolution will look elsewhere. In the absence of sunlight, vision itself becomes a questionable investment. Eyes are expensive organs. They require energy to build, maintain, and operate. In total darkness, natural selection treats unnecessary eyes the way budget cuts treat office perks. Some deep-sea organisms reduce their eyes dramatically. Others lose them entirely. This is not a failure. It is efficiency. Why maintain windows when the lights have been out since before your ancestors existed? But darkness does not mean blindness across the board. It means specialization. Some organisms develop eyes tuned to the faintest possible glimmers, capable of detecting even the weakest flashes of light produced by other creatures. In a sunless world, any light source becomes information, a signal, a warning, or an opportunity. Darkness turns light from a background feature into a currency. Navigation in this environment is also transformed. Without visual landmarks, life relies on other cues. Chemical gradients, water movement, and touch become primary sources of information. The deep ocean is not empty just because we cannot see in it. It is structured in ways that do not rely on sight. To us, darkness feels like absence. To the organisms living there, it is simply the default setting. The disappearance of sunlight also reshapes time. Biological rhythms on the surface often sync to the rising and setting of the sun. In perpetual darkness, those rhythms dissolve or shift to internal clocks. Life continues without a solar schedule, proving that circadian rhythms are not universal rules, but optional features that evolution installs only when useful. What makes this especially humbling is how long this dark world has existed. Sunlight has never reached the Hadal zone, not once in its history. While surface environments changed with climate shifts, asteroid impacts, and evolving atmospheres, the deep ocean remained dark and largely unchanged. It is one of the most stable lighting conditions on Earth, which is a strange sentence to say about total darkness. This stability has consequences. It allows evolutionary strategies to persist for vast spans of time. Adaptations are not constantly being rewritten by fluctuating conditions. Darkness is predictable. In a strange way, it is comforting. The deep ocean teaches us that extremes are not always chaotic. Sometimes they are monotonous, and life adapts not by reacting, but by settling in. Darkness in the Hadal zone is not dramatic. It does not swirl or threaten. It simply exists, pressing in from every direction, erasing the visual world we rely on. And yet, life persists, not by fighting the absence of light, but by redefining what living means when the sun is no longer part of the equation. Cold is easy to underestimate because we experience it as an inconvenience rather than a fundamental force. On the surface, cold means grabbing a jacket, shoving hands into pockets, and complaining loudly about the weather as if it personally offended you. In the deep ocean, cold is not seasonal or temporary. It is a permanent condition, locked in place by physics and geography, quietly governing every process that happens there. By the time you reach the depths of the Hadal zone, temperatures hover just above freezing, creating an environment where warmth is a distant memory, and heat is something that only arrives from within. This cold exists because sunlight does not penetrate the deep ocean, and because water, at depth, is isolated from surface warming. Once water sinks, it can remain cold for centuries, trapped in slow-moving currents that circulate through the abyss. The deep ocean is not refreshed by summer. or comforted by tropical breezes. It is a massive reservoir of cold, dense water that stubbornly resists change. If the surface ocean is a lively conversation, the deep ocean is a long, quiet pause. Temperature has a profound effect on chemistry. As things get colder, molecules move more slowly. Chemical reactions that proceed easily at warmer temperatures begin to drag their feet. Enzymes, the molecular machines that drive life, become less efficient. It is not that reactions stop entirely, but they take their time, like commuters who know they are not being timed. In the Hadal zone, life operates in slow motion compared to the surface, and that slowness defines everything from growth to reproduction. Metabolism, the sum of all chemical reactions that keep an organism alive, is directly tied to temperature. In near-freezing conditions, metabolic rates drop. Energy is conserved. Movements become deliberate rather than frantic. This is not laziness. It is strategy. When energy is limited and reactions are slow, wasting motion is not an option. Deep sea life treats every action like it costs money, because it does. This cold also affects physical properties of materials. Water becomes denser, increasing stability, but reducing mixing. Tissues behave differently when chilled. Flexibility can change, and structures that rely on warmth to remain pliable must adapt. Proteins, in particular, face a challenge. They must remain functional at temperatures that would make many surface proteins seize up like old hinges. Deep-sea organisms solve this by tweaking the composition of their proteins, ensuring they remain flexible enough to do their jobs without falling apart. It is molecular engineering refined by natural selection over geological time. Cold environments also tend to be quiet. Without thermal energy driving vigorous motion, processes unfold subtly. This quietness can be misleading. From the outside, the Hadal zone might appear inactive, almost static. In reality, it is busy in a way that does not announce itself. Life happens slowly, but it does not stop. It simply operates on a different clock, one that does not rush. Reproduction in such cold conditions requires patience. Development takes longer. Growth is measured in years rather than weeks. This extended timeline shapes life histories in profound ways. Organisms invest heavily in survival rather than speed. Longevity becomes more valuable than rapid turnover. In a place where conditions are stable but resources are limited, endurance is the winning strategy. Cold also preserves. Organic material breaks down more slowly at low temperatures, altering how long substances persist in the environment. This can influence nutrient availability and ecological interactions in subtle ways. The deep ocean becomes a place where the past lingers, where traces of earlier events can remain detectable long after they would have vanished in warmer settings. What makes this remarkable is that cold, like pressure and darkness, does not exist in isolation. It interacts with every other environmental factor, amplifying challenges rather than adding new ones. Near freezing temperatures do not just make life uncomfortable, they redefine the rules of biology. They reward efficiency, stability, and resilience over speed and aggression. The Hadal zone teaches us that warmth is not a requirement for life, even though it feels that way to us. Life does not demand comfort. It demands consistency and opportunity. In the deep ocean, cold provides both. It is unchanging, predictable, and relentless. And in response, life has learned to slow down, conserve energy and persist quietly in a world where warmth is a rumor and survival is a long-term commitment. If the surface world is fueled by sunlight and heat, the deep ocean runs on patience. And nowhere is that more evident than in the cold, steady environment of the Hadal zone, where life proves that determination does not always burn hot. Sometimes it survives by staying just above freezing. When scientists finally began exploring ocean trenches directly, they did not find a barren wasteland. Instead, they found a cast of characters so strange that it felt less like biology and more like evolution had been left alone with a box of spare parts and a vague instruction to make it work. Trench animals are not just unfamiliar. They challenge our sense of what an animal is supposed to look like, how it should move, and whether it should have bones that behave like bones at all. Take the Hadal snailfish, one of the deepest living vertebrates ever discovered. At first glance, it looks like something you might accidentally step on in a very unfortunate tide pool nightmare. It is pale, gelatinous, and soft to the point where structure feels like an optional feature. Its body appears almost unfinished, like evolution saved the final render for later. But this softness is precisely the point. In the trenches, rigidity is a liability. The snailfish's body is built to flex, absorb, and tolerate conditions that would turn more confident designs into biological confetti. Snailfish also lack swim bladders, the gas-filled organs that help many fish control buoyancy. Gas behaves badly under extreme conditions, so trench fish simply skip it. Instead, they rely on body composition and subtle movements to maintain position. It is a quiet, understated way of existing, more drifting than swimming, more persistence than performance. Then there are amphipods, the trench's tireless cleanup crew. These small, shrimp-like crustaceans show up everywhere humans look, often in astonishing numbers. Amphipods are scavengers, and they are extremely good at it. When something falls into a trench, amphipods arrive with enthusiasm that borders on alarming. Their bodies are armoured, jointed, and packed with sensory equipment designed to detect opportunity in a vast, dark environment. What makes amphipods especially impressive is their versatility. They are not picky. They consume whatever organic material becomes available, whether it is a natural carcass or something humans would rather pretend never made it into the ocean. Their success lies in adaptability. Amphipods do not wait for ideal conditions. They exploit whatever the trench provides, proving that being flexible beats being fancy when the menu is unpredictable. Some trench creatures push body plans even further into the strange. Sea cucumbers in the Hadal zone abandon the familiar cucumber shape entirely, evolving elongated forms with transparent tissues that reveal their internal organs like biological diagrams. These animals glide slowly across the sediment, ingesting material indiscriminately and extracting whatever nutrients they can. It is not glamorous, but it works, and in the deep ocean, working beats looking impressive every time. There are also worms that build delicate tubes in the sediment, anchoring themselves in place while extending feathery structures to gather particles drifting past. These animals turn stillness into strategy. Instead of chasing food, they let the environment deliver it. In a place where movement costs energy, patience becomes a competitive advantage. One of the most striking patterns among trench animals is how many of them are built around simplicity. Reduced skeletons, soft tissues, minimal ornamentation. These are not signs of inferiority. They are signs of refinement. Every feature that remains serves a purpose. Everything else has been trimmed away by generations of unforgiving conditions. Evolution here is not extravagant. It is brutally practical. At the same time, trench life is not monotonous. Different trenches host different communities, shaped by local conditions and geological context. Some species appear only in specific trenches, suggesting long periods of isolation and independent evolution. These animals are not just deep-sea creatures, they are trench specialists, fine-tuned to narrow ranges that make their existence both impressive and fragile. Studying these animals forces us to confront our biases about what life should look like. We tend to associate complexity with success, rigidity with strength, and familiarity with normality. Trench animals dismantle all of that. They succeed by being soft, slow, and strange. They thrive by ignoring surface world design principles entirely. In the Hadal zone, evolution is not constrained by aesthetics or expectations. It experiments freely, producing organisms that look unfinished, alien, or downright weird to us, yet are perfectly suited to their environment. These animals are not survivors despite their oddness. They are survivors because of it. And the deeper we look, the clearer it becomes that when supervision is minimal, evolution does not behave. It innovates. Pressure may be the most obvious challenge of the Hadal zone, but simply knowing it exists does not explain how anything survives it. The real story happens at scales far smaller than bones, shells, or even cells. It happens in the molecular architecture of life itself. Deep-sea organisms do not resist pressure by being stronger in the traditional sense. They survive by being flexible in ways that make surface biology look stubborn and brittle by comparison. At the heart of this adaptation are proteins, the molecular machines responsible for nearly everything that happens inside a living cell. Proteins fold into precise, three-dimensional shapes, and those shapes determine their function. On the surface, proteins are tuned to operate under relatively gentle conditions, increase pressure dramatically, and those shapes can distort, unfold, or lose efficiency. For most life, this would be catastrophic. For Hadal organisms, it is simply a design constraint. Deep-sea proteins are built differently. Their structures are more flexible, allowing them to maintain function even when squeezed relentlessly from all sides. This flexibility comes from subtle changes in amino acid, composition, and bonding patterns. Think of it as the difference between a glass sculpture and a silicone one. Both can hold a shape, but only one forgives you when you apply force. In the deep ocean, forgiveness is essential. Cell membranes face a similar challenge. These membranes are thin layers of lipids that control what enters and exits the cell. Under high pressure, membranes can become too rigid, compromising their integrity and disrupting cellular processes. Hadal organisms counter this by altering the types of lipids they use. Their membranes remain fluid and functional even when compressed, maintaining the delicate balance that keeps cells alive. It is biochemical problem-solving at its finest, happening invisibly and continuously. One of the most fascinating adaptations involves small organic molecules that stabilize proteins under pressure. These molecules act like molecular shock absorbers, protecting proteins from deformation and loss of function. They do not eliminate pressure, but they help life tolerate it. It is a chemical negotiation with the environment, rather than a direct confrontation, which turns out to be the smarter strategy. This molecular flexibility extends to entire tissues. Deep-sea animals often lack rigid skeletal elements that would be vulnerable under compression. Instead, they rely on soft tissues supported by water and flexible structures. Water, being largely incompressible, becomes an ally rather than a threat. By filling tissues with fluid and minimizing air spaces, these organisms distribute pressure evenly, reducing stress on any single component. Our bones, by contrast, are excellent at resisting gravity, but terrible at negotiating with uniform compression. They would indeed like to file a complaint. Enzymatic reactions also benefit from these adaptations. Enzymes in deep-sea organisms are optimized to function efficiently under conditions that would slow or disable their surface counterparts. Their active sites, the regions where chemical reactions occur, remain accessible and properly shaped, even under intense pressure. This ensures that metabolism, however slow, continues reliably. What is remarkable is that these adaptations do not require exotic chemistry. The building blocks are the same as those used by all life on Earth. The difference lies in arrangement, proportion, and emphasis. Evolution did not invent new materials. It repurposed existing ones with extraordinary precision. This is a reminder that innovation in biology often comes not from new components, but from new ways of using familiar ones. These pressure-resistant features are not universal across all deep-sea life. They are tailored to specific depths and conditions. Organisms living at slightly shallower depths may lack some of the extreme adaptations seen in trench specialists. This gradient highlights how finely tuned these systems are. Even small changes in pressure can drive significant biological differences over evolutionary time. Understanding these mechanisms has implications beyond marine biology. Studying how proteins and membranes remain functional under extreme pressure informs fields ranging from medicine to industrial chemistry. It challenges assumptions about the limits of biological function and expands our understanding of what life can tolerate. In the end, surviving the pressure of the Hadal zone is not about brute strength. It is about compliance without collapse. Deep-sea creatures do not fight pressure. They yield to it intelligently, reshaping their biology at the smallest scales to accommodate forces that would obliterate less adaptable forms. It is a quiet triumph of flexibility over force, and it happens molecule by molecule every second in the deepest places on Earth. If survival in the Hadal zone were a game, finding food would be set to expert mode with the tutorial turned off. Unlike surface ecosystems, where energy arrives daily in the form of sunlight and is quickly converted into lush, moving banquets, the deepest ocean exists on a strict and unpredictable diet. Food here is not grown locally in the traditional sense. It arrives from elsewhere, usually unannounced, and often long after it would have been considered fresh by surface standards. The primary source of food in the Hadal zone is what scientists call marine snow, a steady drizzle of organic particles that sink from the upper ocean. This material includes dead plankton, fecal pellets, discarded body parts, and other biological debris. It sounds unappetizing, because it is, but it is also the nutritional backbone of the deep sea. These particles drift downwards slowly, taking days, weeks, or even months to reach the deepest trenches. By the time they arrive, they have been processed, broken down, and partially consumed by organisms along the way. What remains is not a feast, but it is something. Because marine snow is sparse and diffuse, trench organisms cannot afford to be picky. Many have evolved feeding strategies that emphasize volume over selectivity. Deposit feeders ingest sediment itself, extracting whatever organic material is embedded within it. This turns the seafloor into both plate and pantry. The animals consuming it are not eating dirt for fun. They are filtering calories from a resource that would otherwise be wasted. Scavenging plays a major role as well. When a larger organism dies in the upper ocean and sinks rapidly, it creates a sudden, localized bounty. These events are rare, but transformative. A single carcass can support an entire community for weeks or months. Trench scavengers are exquisitely tuned to detect these opportunities, often arriving quickly despite the vastness of the environment. Speed matters here, not in movement, but in detection and response. Some animals adopt ambush strategies, positioning themselves where food is more likely to accumulate. Trenches are not smooth bowls. Their complex topography creates natural funnels where organic material can collect. By settling in these areas, organisms increase their chances of encountering food without expending precious energy searching for it. In the deep ocean, letting gravity work for you is considered good planning. There are also predators, though their lifestyle looks very different from the high-speed chases we associate with hunting. Deep-sea predators rely on patience and efficiency. They may sit motionless for long periods, conserving energy, waiting for prey to come within range. When they strike, it is decisive. There is no room for wasted effort when meals are infrequent. One of the most fascinating feeding adaptations involves extreme flexibility in diet. Many trench organisms are generalists, capable of consuming a wide range of organic materials. This adaptability ensures survival in an environment where the next meal is never guaranteed to resemble the last. Being a culinary snob is a fast track to extinction in the Hadal zone. Energy conservation is the unspoken rule behind all these strategies. Every movement, every chemical reaction, every attempt to acquire food carries a cost. Deep-sea organisms balance these costs carefully. They grow slowly, reproduce sparingly, and invest heavily in maintenance rather than expansion. Feeding is not about abundance. It is about sustainability. The timing of food arrival also shapes behavior. Because marine snow falls continuously but unpredictably, organisms must be ready to feed whenever the opportunity arises. Some species maintain feeding structures that are always deployed, quietly gathering particles over time. Others rely on episodic feeding, consuming large amounts when food is available and enduring long periods without eating. Both strategies reflect the same reality. Consistency is rare, and resilience matters more than speed. What makes this system remarkable is that it works at all. From a surface perspective, the Hadal zone seems too disconnected from energy sources to support complex life. And yet, through a combination of patience, efficiency, and opportunism, ecosystems persist. They do not flourish in the conventional sense, but they endure. In the deepest ocean, dinner does not come with a schedule or a menu. It arrives late, cold, and unannounced, drifting down from a world that does not know who is waiting below. And still, life adapts, finding ways to turn scarcity into survival, proving once again that biology does not need convenience. It needs persistence. In a world without sunlight, light becomes a tool, and in the deep ocean, bioluminescence is one of the most versatile tools life has ever invented. This glow is not decorative. It is not celebratory. It is not there to make the scenery nicer. Bioluminescence exists because in complete darkness, producing light can mean the difference between eating and starving, hiding and being eaten, or existing quietly and becoming someone else's unexpected snack. Bioluminescence is the ability of living organisms to produce light through chemical reactions inside their bodies. This light is cold, meaning it produces almost no heat, which is ideal when energy is precious. The reaction typically involves a light-producing molecule and an enzyme that triggers it. When they interact, photons are released, and suddenly, something in the dark is no longer invisible. In the Hadal zone, that is a bold move. One of the most common uses of bioluminescence is hunting. Some deep-sea predators use light as bait, luring curious prey toward what looks like a harmless glow in the distance. In a place where visual information is rare, any light can trigger investigation. This strategy relies on deception. The glow promises nothing but curiosity and delivers teeth instead. It is efficient, patient, and deeply unfair, which makes it evolutionarily successful. Other animals use bioluminescence defensively. A sudden flash of light can startle a predator, buying the glowing organism a crucial moment to escape. Some species release clouds of bioluminescent fluid, creating a glowing distraction that confuses attackers. Imagine turning off the lights in a room and throwing a flashbang made of plankton. The effect is disorienting, and in the deep ocean, confusion is a powerful weapon. Camouflage is another surprising use of light. Some organisms produce bioluminescence on their undersides to match the faint glow of light filtering from above, effectively erasing their silhouette when viewed from below. This strategy, known as counter-illumination, turns light into invisibility. It is one of nature's most elegant hacks, using illumination not to be seen, but to avoid being noticed at all. Bioluminescence can also serve as a warning. Certain species glow to signal that they are toxic, unpalatable, or simply not worth the effort. In a place where encounters are rare and costly, clear messaging matters. A glow that says, "Do not bother," can prevent a fatal misunderstanding. This is less about intimidation through size or strength, and more about honesty through light. Communication is another role bioluminescence can play. Some deep-sea animals use specific light patterns to recognize members of their own species. In total darkness, glowing signals become a kind of visual language. These signals must be precise. A misplaced flash could attract the wrong kind of attention. Evolution fine-tunes these patterns carefully, balancing visibility with discretion. What makes bioluminescence especially fascinating is its diversity. Different species produce different colors, intensities, and patterns of light. Blues and greens are most common because they travel farther through water, but variations exist. Some glows pulse, others flicker. Some remain steady, like distant stars pinned to moving bodies. The deep ocean becomes a sparse, living constellation, where each point of light carries intent. Producing light is not free. It costs energy, and in an environment where energy is limited, that cost must be justified. This is why bioluminescence is rarely constant. It is deployed strategically, activated only when needed. The timing, duration, and brightness of a glow are all carefully controlled. In the Hadal zone, glowing unnecessarily is like shouting in a library full of predators. Not all deep-sea animals glow, but a surprising number do. This prevalence suggests that light production offers significant advantages despite its cost. In a world defined by darkness, even a small advantage can shape survival. Bioluminescence turns the absence of sunlight from a limitation into an opportunity. The deep ocean teaches us that light is not inherently good or bad. It is information. It can reveal or conceal, attract or repel, comfort or terrify. In the Hadal zone, light is never neutral. Every glow tells a story, carries a purpose, and reflects millions of years of evolutionary experimentation. Nothing shines without a reason down there. In the deep ocean, sound replaces sight as the primary way the world is sensed. Light fades. Vision becomes unreliable, but sound thrives. Water is an excellent medium for carrying sound waves, far better than air. And in the Hadal zone, sound becomes the long-distance messenger of everything that moves, shifts, or breaks. If the deep sea had a language, it would be spoken in vibrations. Sound travels through water by compressing and expanding molecules, passing energy along like a whisper, moving through a crowded room. In the deep ocean, this process is influenced by pressure, temperature, and depth, creating layers that bend and guide sound in surprising ways. Some sound waves can travel enormous distances, curving through the ocean as if following invisible highways. This makes the deep sea an acoustic environment where events far away can still be heard clearly, if you know how to listen. Scientists learned early on that placing sensitive instruments in the deep ocean allowed them to hear the planet in ways that were impossible from the surface. Earthquakes, even those occurring thousands of kilometers away, send low-frequency vibrations through the ocean. These sounds propagate efficiently, revealing details about seismic events and the structure of Earth's interior. The deep ocean acts as a natural amplifier, carrying the echoes of tectonic movement across vast distances. Listening to the ocean also revealed that it is far from silent. The seafloor creaks, pops, and groans as plates shift and sediments settle. These sounds are not dramatic explosions, but slow, persistent murmurs, like an old building adjusting to its own weight. They remind us that Earth is constantly in motion, even in places that seem frozen and still. Whales, though not inhabitants of the Hadal zone itself, play a surprising role in deep ocean acoustics. Their calls, especially those of large baleen whales, can travel deep into the water column. Hydrophones placed at great depths have recorded these vocalizations, revealing migration patterns, population distributions, and behaviors that would otherwise remain hidden. In a way, the voices of whales stitch together the surface and the deep, carrying biological signals into realms humans rarely visit. Sound is also a crucial tool for exploration. Because light-based imaging is ineffective in extreme depths, scientists rely on sonar to map trenches and locate features. By emitting sound pulses and measuring their return, researchers can reconstruct the shape of the seafloor with remarkable precision. Every map of the Hadal zone is, at its core, a portrait painted with echoes. What makes sound especially valuable is its persistence. Unlike light, which dissipates quickly in water, sound can linger, reflect, and refract. This allows for continuous monitoring of deep ocean environments over long periods. Instruments anchored to the seafloor can listen for months or years, capturing a slow-motion soundtrack of Earth's activity. These recordings reveal patterns that are invisible to short-term observation. However, the acoustic environment of the deep ocean is not just shaped by natural processes. Human activity has introduced new sounds into the ocean, from shipping to industrial operations. Even in remote trenches, faint traces of these noises can sometimes be detected. This intrusion raises questions about how added sound affects deep-sea life, especially organisms that rely heavily on vibration and acoustic cues to navigate their world. For deep-sea organisms, sound is not just background noise. It carries information about movement, proximity, and danger. Vibrations in the water can signal the approach of a predator, or the arrival of an opportunity. Some species are exquisitely sensitive to low-frequency sounds, allowing them to detect events far beyond their immediate surroundings. In the absence of light, hearing becomes a form of foresight. The idea that the deepest parts of the ocean are filled with sound feels counterintuitive. We imagine silence as a companion to darkness, but the Hadal zone defies that expectation. It hums with the slow, steady voice of a living planet. Every tremor, every shift, every distant call adds to a layered acoustic tapestry that is always in motion. By learning to listen, scientists have gained access to a dimension of the deep ocean that sight alone could never provide. Sound reveals not just what the ocean looks like, but how it behaves. It captures the rhythms of Earth itself, echoing through the depths like a reminder that even in the darkest, most remote places, the planet is never truly quiet. Human curiosity has an impressive flaw. It rarely checks whether a place is trying to kill us before deciding to visit. The Hadal zone is one of the clearest examples of this trait. Faced with crushing pressure, eternal darkness, and temperatures that do not care about comfort, humans still decided to go there. But we did not go unprepared. We went inside some of the most carefully engineered machines ever built, because exploring the deepest ocean requires less bravery and more extremely good design. At the core of any deep diving submersible is the pressure sphere. This is the part that holds humans, and it looks deceptively simple. A thick, rounded shell, often made of titanium or specially engineered steel, shaped like a sphere or near-sphere. This shape is not an aesthetic choice. It is physics. A sphere distributes pressure evenly across its surface, preventing stress from concentrating in one area. Flat surfaces would fail. Corners would fail faster. The ocean punishes poor geometry without hesitation. The walls of these spheres can be several inches thick, and every millimeter matters. Too thin, and the sphere collapses. Too thick, and the vehicle becomes too heavy to manage. Engineers walk a narrow line between strength and practicality, calculating exactly how much material is needed to survive depths where the pressure is measured in tons per square inch. These calculations are not theoretical. They are tested repeatedly because mistakes at those depths do not come with second chances. Windows are another challenge. Humans want to see where they are going, which is a deeply inconvenient desire in the Hadal zone. Transparent materials must be strong enough to withstand enormous pressure without cracking or deforming. Acrylic has proven surprisingly effective, not because it is harder than glass, but because it flexes slightly under pressure rather than shattering. These windows are thick, curved, and carefully polished, turning a simple act of looking outside into a triumph of materials science. Life support systems add another layer of complexity. Inside the pressure sphere, conditions must remain stable for hours, sometimes days. Oxygen levels are carefully controlled. Carbon dioxide is scrubbed from the air, using chemical systems that operate silently in the background. Temperature must be regulated, because the surrounding cold would otherwise seep in relentlessly. Every breath taken inside a submersible is part of a carefully managed ecosystem. Propulsion and control systems face their own set of problems. Motors must function reliably under extreme pressure, often enclosed in oil-filled housings that equalize internal and external forces. Electrical components are sealed, protected, and tested extensively. Cables, joints, and connectors are all potential failure points, and each one must be designed to survive conditions that would crush ordinary equipment instantly. Navigation in the deep ocean is another puzzle. Traditional GPS does not work underwater, let alone at extreme depths. Submersibles rely on a combination of inertial navigation, acoustic positioning, and pre-mapped data to know where they are. It is a bit like navigating a city while blindfolded, using only echoes and careful bookkeeping. Precision matters because the margin for error is small and the environment is unforgiving. Human exploration of the Hadal zone has always been cautious and incremental. Early dives were brief and limited, focused on proving that survival was possible. Over time, confidence grew and missions became more ambitious. Each successful dive built trust in the machines, but that trust was never blind. Engineers and pilots know exactly how much pressure is bearing down on them at any given moment. It is a constant, unignorable fact of the journey. What makes these expeditions especially remarkable is how quiet they are. There is no dramatic roaring of engines or cinematic music swelling in the background. Inside a submersible, the experience is calm, almost meditative. The danger is real, but it is managed through preparation and design rather than adrenaline. Exploration becomes a dialogue between human curiosity and engineering discipline. The Hadal zone does not yield easily. It demands respect, precision, and humility. Submersibles are not expressions of dominance over the environment. They are compromises, carefully negotiated spaces where humans can exist temporarily in a place that fundamentally does not want us there. In building these machines, humans did not conquer the deep ocean. We learned how to visit it briefly, under strict conditions, and with a deep appreciation for the forces at play. Every dive is a reminder that exploration is not about overcoming nature through strength, but about understanding it well enough to survive in its presence, even if only for a few hours at the bottom of the world. The Challenger Deep is not just the deepest known point in the ocean, it is the place humans go when we want to ask life a very direct question. Are you absolutely sure you can live here? Located at the southern end of the Mariana Trench, this region represents the most extreme combination of depth, isolation, and environmental severity on Earth's surface. It is the ocean's final exam, and biology keeps showing up with answers written in permanent ink. Early exploration of the Challenger Deep was motivated by a desire to reach the bottom. But what scientists found there shifted the goal entirely. The real revelation was not the depth itself, but the unmistakable presence of life. Sediment samples retrieved from the seafloor contained organisms, chemical signatures of biological activity, and clear evidence that this was not a sterile place. It was quiet, sparse, and subtle, but it was alive. What surprised researchers most was not just that life existed, but that it was active. Cells were metabolizing, reproducing, and interacting with their environment. This forced a re-evaluation of long-held assumptions about the limits of biology. The Challenger Deep demonstrated that there is no single threshold beyond which life simply gives up. Instead, life adjusts, reshapes itself, and continues, even when conditions seem designed to discourage it. One of the key insights from studying this region was that extreme environments do not necessarily simplify ecosystems to the point of triviality. While the number of species may be lower than in shallower waters, the organisms that do exist are highly specialized and finely tuned. Their adaptations are not crude compromises. They are precise solutions to very specific problems. This precision suggests long periods of evolutionary refinement rather than desperate last-minute survival. The sediment at the bottom of the Challenger Deep told its own story. It contained organic material, microbial communities, and chemical gradients that indicated ongoing biological processes. Life here was not merely surviving in isolation. It was integrated into a functioning, if minimal, ecosystem. This shattered the idea that extreme depth equates to ecological insignificance. Another major lesson came from comparing life in the Challenger Deep to life in slightly shallower trench regions. The differences were subtle, but important. Species found here were not simply deeper versions of familiar deep-sea organisms. Many were distinct, suggesting that the Challenger Deep acts as a kind of biological island, isolated by depth and geography. This isolation allows unique evolutionary paths to emerge, reinforcing the idea that depth itself can be a driver of biodiversity. Perhaps the most humbling discovery was how unremarkable life appeared to be about its circumstances. There was no sign that organisms were barely hanging on, no evidence of constant crisis. Instead, biology seemed settled. The Challenger Deep was not an emergency shelter, it was home. That realization reframed how scientists think about habitability, not just on Earth, but anywhere. Exploration of the Challenger Deep also revealed how much we had underestimated the resilience of cellular life. Microorganisms in this region showed metabolic activity under conditions that challenged laboratory experiments. This pushed scientists to reconsider the boundaries used to define where life could exist. The deep ocean was no longer an outlier. It became a proof of concept. There is also a psychological impact to studying this place. Knowing that life persists at the deepest point on our planet changes how we perceive Earth itself. The planet becomes less fragile in one sense, more stubborn. It has systems that continue operating long after comfort, familiarity, and human relevance have disappeared. The Challenger. Deep does not care whether it is observed. Life there does not perform for us. It simply continues. This stubbornness of biology is not heroic in a dramatic sense. It is quiet, methodical, and relentless. Cells divide. Chemical reactions proceed. Energy flows through systems that have no awareness of how extreme their environment appears from the surface. The Challenger. Deep teaches us that life does not need encouragement. It needs opportunity, however small, and time. In the end, the Challenger Deep stands as a reminder that the limits we imagine are often reflections of our own experience, not universal truths. Biology does not share our discomfort. It does not flinch at depth or isolation. It adapts, persists, and occupies even the most improbable corners of our planet. And in doing so, it forces us to rethink what it truly means for a place to be uninhabitable. For a long time, the Hadal zone was imagined as one of the last untouched places on Earth. So deep, so distant, and so hostile that it seemed immune to human influence. After all, if it takes specialized machines just to visit, surely our trash could not possibly make it there. Unfortunately, the ocean does not respect our assumptions, and gravity is an extremely reliable delivery service. When scientists began sampling trench environments more carefully, they discovered something deeply uncomfortable. Humanity had arrived ahead of schedule. One of the earliest shocks came from sediment samples pulled up from extreme depths. Mixed in with the expected minerals and organic material were unmistakable traces of synthetic chemicals. Compounds used in industrial manufacturing, flame retardants, and long-band pollutants showed up in places where no human had ever set foot. These chemicals do not dissolve easily, do not break down quickly, and do not politely stay where they are released. Instead, they hitch a ride on particles sinking through the ocean, slowly accumulating in the deepest parts of the planet, like an unwanted inheritance. Plastic, of course, made its appearance too. Microplastics, tiny fragments formed as larger plastic items break down, have been found in trench sediments and inside deep-sea organisms. These particles are small enough to be eaten accidentally and persistent enough to remain in the environment for decades or longer. The idea that animals living nearly 11 kilometers below the surface are ingesting fragments of packaging designed for convenience is both surreal and unsettling. What makes trenches particularly vulnerable is their shape and location. Trenches act as natural collection zones. Material sinking through the ocean tends to accumulate there, funneled by topography and gravity. This means that pollutants introduced at the surface can become concentrated at depth. The Hadal zone is not isolated from the rest of the ocean. It is downstream from it. The discovery of pollution in trenches forced scientists to rethink the scale of human impact. Pollution is often discussed in terms of visible damage, like oil spills or floating debris. But the Hadal zone reveals a quieter, more pervasive form of influence. Chemicals and microplastics do not announce their presence. They blend into the environment, interacting with biological systems in ways that are difficult to observe, but potentially profound. One particularly troubling finding involved the accumulation of pollutants in the tissues of trench animals. Even in environments where food is scarce and energy flows slowly, these substances made their way into biological systems. This suggests that pollution is not just present, but biologically active, entering food webs that were once assumed to be isolated from surface activities. The irony is hard to ignore. Some of the same traits that allow life to survive extreme depth, such as slow metabolism and long lifespans, may make deep-sea organisms especially vulnerable to pollution. Slow biological processes mean slower detoxification. Long lifespans mean more time for harmful substances to accumulate. What looks like resilience in one context can become liability in another. Pollution in trenches also raises ethical questions about exploration itself. Every expedition risks introducing contaminants. No matter how careful scientists are, equipment, materials, and even trace residues can leave an imprint. This does not mean exploration should stop, but it does mean it must be conducted with an awareness that no place is truly beyond our reach or responsibility. Perhaps the most sobering lesson is what trench pollution says about connectivity. The Hadal zone feels distant, but it is deeply connected to surface systems. What happens on land and in coastal waters does not stay there. It moves, settles, and accumulates in places we may never see directly. The ocean is not a series of separate compartments. It is one continuous system, and the trenches are part of its memory. Finding pollution in the deepest ocean strips away the comforting illusion that remoteness equals protection. There is no depth at which human influence automatically disappears. The Challenger, deep and other trenches are not sealed vaults. They are repositories, quietly recording the byproducts of modern civilization. This realization does not diminish the wonder of the Hadal zone, but it complicates it. The deepest parts of the ocean are still extreme, still mysterious, still filled with life that defies expectations. But they are no longer untouched. They carry our fingerprints, not because we intended to put them there, but because the systems we rely on do not have off switches. In the end, trench pollution teaches us that exploration is not just about discovering what exists. It is about understanding what we have already changed. Even at the bottom of the world, the story of the deep ocean now includes us, whether we like it or not. If the Hadal zone had a most valuable player, it would not be a fish, a crustacean, or anything you could recognize without a microscope. It would be microbes. Invisible, abundant, and outrageously stubborn, trench microbes are the foundation upon which deep-sea ecosystems quietly depend. Studying them has completely rewritten what scientists thought they knew about the boundaries of life, mostly by revealing that those boundaries were imaginary to begin with. Microbes in the deepest ocean live embedded in sediments, drifting in water and clinging to particles that sink from above. These organisms face every extreme at once, yet they remain metabolically active. Early assumptions held that life at such depths would be dormant at best, frozen in a kind of biological pause. Instead, researchers found microbial communities carrying out chemical reactions, cycling elements, and supporting entire food webs from the bottom up. One of the most important revelations was that these microbes do not rely on sunlight, directly or indirectly, in the way surface ecosystems do. Their energy sources are chemical rather than solar. They extract energy from reactions involving compounds such as methane, sulfur, or ammonia. These reactions may seem insignificant, but in the Hadal zone, they are enough. Microbes make a living off chemistry that most organisms would ignore entirely. The efficiency of trench microbes is remarkable. They operate at energy levels so low that they challenge laboratory measurements. Some reactions occur at rates that would be considered negligible elsewhere, yet over long periods, they sustain entire populations. This forced scientists to rethink what enough energy actually means for life. The deep ocean showed that life does not need abundance. It needs consistency. Another discovery that shifted scientific thinking was the sheer diversity of microbial life in trenches. Far from being uniform, microbial communities vary between trenches and even between layers of sediment within the same trench. This diversity suggests long-term stability and localized evolution. Microbes are not just surviving passively, they are adapting, diversifying, and specializing in response to microenvironments that differ subtly in chemistry and structure. Trench microbes also demonstrated an extraordinary ability to repair themselves. Damage to DNA is inevitable under extreme conditions, yet these organisms possess robust repair mechanisms that allow them to maintain genetic integrity over time. This resilience is not flashy, but it is essential. It ensures continuity in environments where mistakes are costly and recovery options are limited. The study of these microbes had implications far beyond marine biology. It reshaped how scientists think about habitability in general. If life can persist at extreme depth, under crushing pressure, without sunlight, and with minimal energy, then the range of environments considered potentially habitable expands dramatically. The deep ocean became a model for thinking about life in places previously dismissed as impossible. Microbial activity in trenches also plays a role in global processes. By cycling carbon and other elements, these organisms influence how material moves through the ocean over geological time. Their work is slow but persistent, contributing to long-term planetary balance. They are not just surviving at the edges, they are participating in Earth's systems in ways that matter. Perhaps the most humbling aspect of trench microbes is how unassuming they are. They do not build structures, produce light, or display behaviors that draw attention. Their impact is quiet and cumulative. They alter their environment molecule by molecule, reaction by reaction. In doing so, they remind us that importance in biology is not measured by size or visibility. Studying these microbes required scientists to confront their own biases. Life had been framed in terms of complexity, movement, and growth. Trench microbes defy that framing. They thrive by being efficient, patient, and relentless. They prove that life's greatest strength is not speed or power, but persistence. In the Hadal zone, where most things would instantly give up, microbes do not just survive. They thrive in a way that feels almost philosophical. They occupy a niche so extreme that it strips life down to its essentials, revealing what is truly necessary and what is merely optional. And in doing so, they quietly expand the definition of life itself. For most of human history, earthquakes felt like random acts of planetary bad manners. The ground shook, buildings fell over, and people understandably asked what they did to deserve it. Only much later did we realize that earthquakes are not spontaneous tantrums, but symptoms of a planet that is constantly in motion. The deepest parts of the ocean, especially trenches, turned out to be one of the best places to listen in on that motion and finally understand what Earth has been doing beneath our feet all along. Ocean trenches mark the boundaries where tectonic plates collide and interact. These boundaries are not neat seams. They are chaotic zones where enormous slabs of rock grind, bend, and descend into the mantle. The Hadal zone sits directly above these interactions, making it a front-row seat to the mechanics of plate tectonics. By studying the deep seafloor, scientists gained access to the physical record of how plates move, how stress builds, and how that stress is eventually released. One of the most important discoveries came from mapping trench structures in detail. High-resolution surveys revealed complex fault systems, folded sediments, and fractured crust that could not be explained by simple plate movement alone. These features showed that subduction is not a smooth slide, but a messy, stop-and-go process. Plates lock together, accumulate stress, then slip suddenly, producing earthquakes. The deep ocean preserves evidence of these cycles far better than many land environments, where erosion quickly erases the past. Sediments in trenches act like geological notebooks. Layer by layer, they record disturbances caused by seismic events. Underwater landslides triggered by earthquakes leave distinct signatures in the sediment record. By analyzing these layers, scientists can reconstruct a history of past earthquakes, including events that occurred long before humans were around to feel them. This turns trenches into archives of seismic activity stretching back thousands or even millions of years. Deep sea instrumentation has also transformed earthquake monitoring. Sensors placed on or near the seafloor can detect subtle movements and vibrations that never reach land-based stations. This provides a clearer picture of how seismic energy travels through Earth's crust and mantle. In some cases, these instruments detect slow slip events, where plates move gradually without producing a dramatic earthquake. These events release energy quietly, like a pressure valve opening slowly instead of exploding. Understanding these slow processes has reshaped how scientists think about earthquake risk. Not all tectonic movement is catastrophic, but all of it matters. The deep ocean reveals that Earth's crust is constantly adjusting, redistributing stress in ways that are invisible at the surface. Earthquakes are not isolated incidents. They are moments in an ongoing negotiation between moving plates. Trench exploration also shed light on how earthquakes interact with the ocean itself. Large seismic events can reshape the seafloor, alter trench geometry, and trigger massive sediment flows. These changes affect how material moves through the deep ocean and how ecosystems respond to sudden disturbance. Earthquakes are not just geological events, they are ecological ones, capable of reshaping habitats in an instant. Studying the Hadal zone also clarified the relationship between plate tectonics and volcanism. As plates descend into the mantle, they carry water and other materials with them. This influences melting processes deep within Earth, contributing to volcanic activity elsewhere. Trench systems are not isolated features. They are integral parts of a global network of crustal recycling that drives much of Earth's surface activity. Perhaps the most profound lesson from deep-sea geology is that Earth is never finished. The crust beneath the ocean is younger, more dynamic, and more transient than much of the continental crust. It is constantly being created, destroyed, and reshaped. Trenches are not scars from past events. They are active processes, evidence that the planet is still building itself. By studying the deepest ocean, scientists moved beyond surface observations and gained a three-dimensional understanding of Earth's behavior. Earthquakes stopped being mysterious jolts and became understandable consequences of long-term motion. Plate tectonics stopped being abstract diagrams and became tangible, measurable processes. The Hadal zone reminds us that the ground beneath our feet is not solid in the way we imagine. It is part of a restless shell floating on a dynamic interior. And by listening to the deep ocean, we learned that Earth's crust is not quiet, stable, or still. It is alive with movement, patiently reshaping the planet, one tremor at a time. For a long time, the search for life beyond Earth focused on finding places that looked familiar. Scientists looked for planets with blue skies, mild temperatures, and liquid water at the surface, essentially asking the universe to copy Earth's homework. The Hadal zone forced a radical shift in that thinking. By revealing how life thrives under crushing pressure, permanent darkness, and minimal energy, Earth's deepest ocean became a training ground for imagining life in places that look nothing like home. One of the most important lessons trench biology taught us is that life does not need sunlight. This realization opened the door to astrobiology in a dramatic way. Many of the most promising locations for extraterrestrial life, such as icy moons orbiting giant planets, are completely cut off from direct starlight. Beneath thick ice shells, moons like Europa and Enceladus are thought to hide vast subsurface oceans. These environments would be dark, cold, and pressurized, sounding eerily familiar to scientists who study the Hadal zone. The comparison does not end with darkness. Subsurface oceans on icy moons would also experience intense pressure due to the weight of ice above. Trench organisms demonstrate that pressure alone is not a deal breaker for life. If biology on Earth can adapt its proteins, membranes, and metabolic processes to survive extreme compression, then similar strategies could, in principle, evolve elsewhere. The Hadal zone provides a real-world example that these adaptations are not hypothetical. They exist. Energy is another crucial connection. In the deep ocean, life persists without relying on sunlight, drawing energy from chemical reactions instead. This aligns closely with what astrobiologists expect in alien oceans. On icy moons, interactions between water and rocky interiors could provide chemical energy sources capable of supporting life. Trench microbes show that such energy sources do not need to be abundant. They only need to be reliable. Studying deep-sea life also reshaped assumptions about ecosystem complexity. Early models of extraterrestrial life imagined simple microbial systems at best. Trench ecosystems challenge that minimalism. While not lush, they are structured, with food webs, interactions, and specialization. This suggests that alien oceans, if they host life, might support more than just isolated cells drifting aimlessly. Complexity does not require sunlight. It requires time and stability. Another important contribution of trench biology is methodological. Exploring the Hadal zone forced scientists to develop tools and techniques for studying life in environments that are inaccessible and hostile. These same approaches inform how future missions might search for life beyond Earth. Sampling strategies, contamination control, and remote sensing techniques developed for deep ocean research are directly applicable to astrobiological exploration. There is also a philosophical shift that comes from studying Earth's extremes. It teaches humility. The Hadal zone reminds us that life can look radically different from our expectations. Alien life, if it exists, may not resemble anything familiar. Trench organisms prepare scientists to recognize life by function rather than form, focusing on chemical signatures, energy use, and environmental interactions instead of familiar shapes. Deep-sea research also emphasizes patience. Processes in the Hadal zone unfold slowly, over long timescales. This parallels the conditions expected in many extraterrestrial environments, where energy flows are low and biological activity may be subtle. Recognizing signs of life in such settings requires careful observation and a willingness to accept that biology does not always announce itself loudly. Perhaps the most powerful connection between trench biology and astrobiology is psychological. The Hadal zone demonstrates that Earth still holds environments that feel alien despite being right here. Studying these places trains scientists to think beyond surface biases and imagine worlds shaped by entirely different constraints. It expands the scientific imagination in a grounded, evidence-based way. When we look at icy moons through the lens of deep ocean biology, they stop being abstract possibilities and start feeling plausible. The Hadal zone acts as a bridge between Earth and the cosmos, showing that life is not confined to gentle conditions. It adapts, innovates, and persists wherever physics allows chemistry to cooperate. In this way, exploring Earth's deepest trenches does more than satisfy curiosity about our own planet. It prepares us for one of humanity's biggest questions. Are we alone? By studying life at the bottom of our own ocean, we learn how to recognize life, even when it hides in the dark, beneath layers of ice, on worlds far from the warmth of a sun. The story of deep-sea exploration is often told as a series of triumphs, heroic dives, record-breaking descents, and dramatic photographs from impossible depths. But beneath those highlights lies a quieter, more important story. One written in cracked housings, imploded instruments, and designs that did not survive their first encounter with reality. In the deep ocean, failure is not an embarrassment. It is a teacher, and it has shaped every piece of technology that now dares to visit the Hadal zone. Early deep-sea technology was built with optimism that bordered on denial. Engineers knew the ocean was deep and pressurized, but translating that knowledge into reliable machines was another matter entirely. Early devices failed in spectacular and humbling ways. Casings collapsed, seals leaked, electronics shorted out under conditions they were never meant to endure. Each failure made one thing very clear. The deep ocean does not forgive assumptions. One of the most important lessons learned was that designing for strength alone is not enough. Early designs often focused on making things thicker, heavier, and more rigid. This approach worked up to a point, then failed catastrophically. Engineers eventually realized that survival at extreme depth requires balance, not brute force. Flexibility, redundancy, and pressure compensation became just as important as raw strength. Pressure testing became a discipline of its own. Components were crushed in controlled environments to identify weak points long before they ever touched seawater. Engineers learned to expect failure, to design tests specifically to provoke it, and to treat every broken part as valuable data. In the deep-sea world, a failed test is a success if it happens before deployment. Materials. Science advanced rapidly as a result of these challenges. Alloys were refined. Polymers were tested in extreme conditions. Even simple elements like adhesives had to be reconsidered. Some materials that performed beautifully on land behaved unpredictably under pressure, while others exceeded expectations. Each discovery reshaped design philosophies, pushing technology towards solutions that prioritized reliability over elegance. Electronics posed a particularly stubborn problem. Water and electricity are famously incompatible, and pressure only makes that relationship worse. Engineers responded by isolating sensitive components in oil-filled compartments that equalize pressure rather than resist it. This approach turned pressure from an enemy into a neutral factor, allowing electronics to function normally even at extreme depths. It was a conceptual shift born directly from earlier failures. Robotics also evolved through trial and error. Early remotely operated vehicles struggled with mobility, control, and durability. Cables failed. Thrusters malfunctioned. Sensors gave confusing data. Each setback forced improvements, leading to more agile, autonomous systems, capable of navigating complex terrain with minimal human input. Modern deep-sea robots are not just tougher. They are smarter, because engineers learned where human control was a liability. Perhaps the most valuable lesson learned from failure was humility. The deep ocean exposed how little margin for error exists at extreme depth. This forced a culture of caution, documentation, and iterative improvement. Designs were no longer rushed. Redundancy became standard. Every component had to justify its presence. This mindset spilled over into other fields, influencing engineering approaches far beyond oceanography. Failure also shaped how missions are planned. Instead of assuming success, teams now plan for partial success, degraded performance, and recovery scenarios. Data collection systems are designed to transmit information incrementally. So even if a mission ends early, something is gained. This philosophy ensures that exploration remains productive, even when conditions refuse to cooperate. What makes this evolution especially compelling is that it mirrors the environment being explored. Just as life in the Hadal zone adapts through persistence and refinement, so too does the technology built to study it. Each failure removes a weakness, leaving behind designs better suited to their environment. Progress is slow, deliberate, and cumulative. Deep-sea exploration technology did not advance because engineers always got it right. It advanced because they paid attention when they got it wrong. The ocean provided immediate feedback, and that feedback was brutally honest. Designs that worked survived. Designs that did not were erased without ceremony. In the end, the machines that now reach the deepest parts of the ocean are monuments not to human dominance, but to human learning. They are the result of countless failures transformed into understanding, and every successful dive carries with it the quiet legacy of all the ones that did not make it back, reminding us that in the deepest places on Earth, failure is not the opposite of progress. It is the path to it. The deep ocean has a very specific teaching style. It does not give warnings, second chances, or encouraging feedback. It simply applies physics and waits to see what survives. Every piece of technology sent into the Hadal zone eventually learns this lesson, usually the hard way. And in deep sea exploration, the hard way has been far more educational than the easy one. Early attempts to reach extreme depths were driven by confidence and curiosity, sometimes in equal measure. Engineers knew the numbers on paper. They understood pressure, corrosion, cold, and isolation. What they did not fully understand was how these forces collaborate like an organized crime syndicate. Pressure weakens seals, cold stiffens materials, corrosion exploits microscopic flaws, and isolation ensures no one can fix mistakes on the fly. The deep ocean does not attack technology one problem at a time. It multitasks. Some of the earliest deep-sea devices failed before they even reached their target depth. Housings collapsed inward with stunning efficiency, turning carefully engineered instruments into compact, metallic regrets. These implosions were not subtle. They were violent reminders that theoretical strength and real-world strength are very different things. Each crushed device provided data that could never have been obtained in a laboratory alone. One of the first major lessons was that resisting pressure is not always the smartest strategy. Early designs relied heavily on rigid structures meant to keep the ocean out. This worked until it didn't. Engineers eventually realized that allowing pressure in, under controlled conditions, could be far safer than trying to hold it back entirely. Pressure-tolerant designs emerged, where components are bathed in oil or other fluids that equalize internal and external forces. Instead of fighting the ocean, technology learned to coexist with it. Failures also forced innovation in materials. Metals that performed well at the surface behaved unpredictably under extreme compression. Some cracked. Others deformed slowly over time. Polymers became brittle. Seals that looked perfect during assembly failed after hours in the deep. Each malfunction pushed engineers toward better alloys, smarter material combinations, and designs that anticipated long-term stress rather than short-term success. Electronics posed a particularly cruel challenge. The deep ocean is cold, dark, and wet, which happens to be exactly what electronics dislike most. Early systems suffered from leaks so small they were invisible, yet catastrophic. Over time, engineers learned that perfection was unrealistic. Redundancy became essential. Critical systems were duplicated. Failures were assumed, not feared. If one circuit failed, another was ready to take over without complaint. Cameras, often the public face of deep-sea exploration, were especially temperamental. Lenses fogged, housings cracked, and lights failed just when something interesting appeared. Each disappointing dive taught engineers how to improve lighting angles, reduce heat buildup, and protect sensitive optics. The stunning images we have today exist because many earlier ones never happened. Robotic systems also evolved through disappointment. Early remotely operated vehicles struggled with navigation, stability, and communication delays. The deep ocean is not a smooth, empty space. It is uneven, unpredictable, and littered with obstacles. Failed maneuvers and lost equipment forced improvements in control systems and autonomy. Modern deep-sea robots make decisions on their own because engineers learned that direct human control is not always fast or reliable enough. Perhaps the most important outcome of repeated failure was a cultural shift. Deep-sea engineering became cautious, iterative, and deeply analytical. Designs were tested, broken, redesigned, and broken again. Each failure was documented in detail. Nothing was dismissed as bad luck. In an environment this unforgiving, every mistake has a cause, and finding it is the only way forward. This mindset influenced mission planning as well. Instead of assuming everything would work, teams began designing missions that could still succeed partially if systems failed. Data transmission was prioritized early in dives. Instruments were built to record information continuously rather than waiting for a perfect moment. Even a short-lived mission could yield valuable insights if planned wisely. What makes this story compelling is that progress did not come from spectacular victories. It came from persistence. The technology that now reaches the deepest parts of the ocean is not flawless. It is simply better adapted. It reflects a deep respect for the environment it enters, shaped by countless reminders of what happens when that respect is missing. In the end, the Hadal zone did not just reveal secrets about the ocean, it reshaped how humans build machines. It taught engineers that success is not the absence of failure, but the accumulation of lessons learned from it. And every time a submersible returns intact from the abyss, it carries with it the quiet acknowledgement that it survived, because others did not. When people talk about resilience, they often imagine dramatic acts of survival. Struggle, triumph, and a victory soundtrack playing somewhere in the background. The Hadal zone offers a very different definition. Down there, resilience is quiet. It is not about winning. It is about continuing. Life in the deepest ocean does not conquer its environment. It endures it, patiently, one moment at a time. The Hadal zone strips life down to its most basic requirements. There is no excess energy, no wasted motion, no room for inefficiency. Everything that exists there has been filtered by conditions so severe that only the essentials remain. Studying this environment forces us to confront what resilience actually looks like when nothing is easy and nothing is guaranteed. One of the most striking lessons is that resilience does not always mean toughness. Many deep-sea organisms are physically delicate by surface standards. Their bodies are soft, flexible, and easily damaged outside their native pressure. Strength in this context is not rigidity. It is compatibility. Life adapts not by resisting the environment, but by aligning with it as closely as possible. Adaptation in the Hadal zone also challenges our ideas about speed and progress. Evolutionary change here happens slowly. Energy is limited, reproduction is measured, and growth is gradual. Yet over long periods, these slow processes produce organisms exquisitely tuned to their surroundings. The Hadal zone teaches that resilience is often the result of patience rather than rapid response. Another powerful insight is that survival does not require comfort. Life in the deepest ocean exists in a constant state of constraint. Temperatures are low, resources are scarce, and conditions rarely improve. Yet life persists without complaint or expectation of better days. This reframes how we think about habitability. Conditions do not need to be pleasant, they need to be consistent. The Hadal zone also reveals that resilience is not an individual trait alone. It is an ecosystem property. Organisms are interconnected through food webs and chemical cycles that allow energy and matter to move efficiently through the system. When one component changes, others adjust. This networked resilience allows the system as a whole to persist even when individual members are lost. There is also a lesson in humility. Humans often place themselves at the top of a hierarchy of resilience, armed with technology and intelligence. Yet we cannot survive in the Hadal zone without elaborate machines and careful planning. Life that evolved there needs none of that. It simply exists, following rules written by physics and chemistry rather than engineering. Studying life under such extreme conditions also highlights the creativity of adaptation. Solutions that seem bizarre at the surface make perfect sense in context. Unusual body shapes, slow metabolisms, and unconventional life strategies are not compromises. They are optimizations. The Hadal zone teaches that there is no single correct way to live. There are only ways that work. Perhaps the most profound lesson is psychological rather than biological. The Hadal zone confronts us with a version of life that does not rely on hope, ambition, or progress as we define them. It survives without expecting change. In doing so, it challenges the assumption that life must always strive upward or outward. Sometimes, resilience is about staying exactly where you are. This perspective has implications beyond science. It invites reflection on how humans respond to adversity. We often equate resilience with dramatic transformation or visible strength. The Hadal zone suggests another model. Adapt quietly. Use what is available. Conserve energy. Persist. Life at extreme depth also reminds us that survival is not a guarantee, even with adaptation. Many organisms likely fail before successful strategies emerge. Resilience is not the absence of loss. It is what remains after loss has done its work. The Hadal zone is not a paradise. It is a proving ground. In the end, the deepest ocean teaches us that life does not need ideal conditions to endure. It needs opportunity, stability, and time. Given those, life will find a way to exist in places that seem utterly hostile. The Hadal zone stands as a testament to life's quiet defiance of impossibility, a reminder that persistence can be powerful even when it whispers instead of shouts. By the time we reach the end of this journey, it becomes clear that the Hadal zone is not just a place. It is a perspective, a way of seeing Earth that strips away familiarity and forces us to confront how little of our planet we truly experience. The deepest ocean does not shout for attention. It sits quietly at the bottom of the world, shaping systems, hosting life, and recording history without ever asking to be noticed. Everything we have learned from the Hadal zone points to one central truth. Earth is far more complex, connected, and resilient than it appears from the surface. The deepest trenches are not isolated curiosities. They are active participants in planetary processes, influencing geology, chemistry, biology, and even how we think about life beyond our world. The ocean's greatest depth turns out to be one of its greatest teachers. What makes the Hadal zone so powerful is how it challenges assumptions. It defies the idea that life needs comfort. It rejects the notion that remoteness equals irrelevance. It dismantles the belief that we have already discovered the most important parts of our planet. Time and again, exploration of the deepest ocean has revealed surprises that force scientists to rewrite what they thought they knew. The Hadal zone also reframes humanity's place on Earth. From the surface, it is easy to feel dominant. We build cities, cross oceans, and leave marks that are visible from space. At the bottom of the ocean, that sense of dominance dissolves. Human presence becomes temporary, fragile, and conditional. The planet feels older, larger, and far less concerned with our schedules or priorities. Yet the story of the Hadal zone is not one of insignificance. It is one of connection. the deepest ocean is linked to surface processes through sinking material, tectonic movement, and global cycles that operate over immense time scales. What happens at the surface eventually reaches the depths. What happens in the depths feeds back into the surface world. There is no true separation. This realization carries responsibility. The Hadal zone teaches us that there are no truly untouched places left on Earth. Even the most extreme environments bear the imprint of human activity. Understanding this does not diminish the wonder of exploration, it deepens it. It reminds us that discovery comes with stewardship, whether we intended it or not. There is also a deeply human element to this story. Exploring the deepest parts of the ocean is not just a scientific endeavor. It is an emotional one. It taps into the same curiosity that drove humans to explore continents, skies, and space. It speaks to our desire to understand where we live, even when that understanding reveals our limitations. The Hadal zone shows us that progress is not always loud or fast. Some of the most important insights come from places where change happens slowly and quietly. Life there moves at a different pace, teaching patience and respect for processes that operate beyond human timescales. In a world obsessed with speed, this lesson feels especially relevant. Perhaps most importantly, the deepest ocean reminds us that Earth is still full of mystery. In an age where it often feels like everything has been mapped, measured, and explained, the Hadal zone stands as evidence that there are still frontiers beneath our feet. These frontiers are not waiting to be conquered, they are waiting to be understood. Understanding the Hadal zone also changes how we think about ourselves. It highlights the adaptability of life, the ingenuity of human exploration, and the fragility that underlies both. It invites humility without discouragement, curiosity without arrogance. It encourages us to ask better questions, not just more questions. As we return to the surface, carrying the lessons of the deepest ocean with us, one thing becomes clear. The Hadal zone is not important because it is extreme. It is important because it reveals truths that apply everywhere, about resilience, about connection, about the quiet persistence of systems far older than we are. The deepest part of the ocean is not just a destination, it is a reminder that our planet is alive in ways we are only beginning to understand. That exploration is as much about perspective as it is about place, and that sometimes, to truly understand Earth and ourselves, we have to look not upward or outward, but all the way down,